the 4th. We have survived election day, kind of. It's still not really over yet. I'm recovered from my 2-hour standing in line for my opportunity to vote. I've never, ever seen lines this long. Although they say 2016 there was actually a greater percentage of people that voted, but I didn't have to wait in line like this. So anyway, it's another day. It's a day for us to go a little bit deeper in bonding, covalent bonding, okay? Understanding how things overlap, how orbitals bond, this whole thing of hybridization. Somebody try to just kind of give me a very general overview of what hybridization is.
A small end of the 8 and a big end of the 8.
Okay, so the 8 being what type of orbital? If we take an s orbital, which is really spherically shaped, so it covers the whole atom, okay, so it's 3-dimensional. And then we hybridize that with the p orbital, which I think was referred to as the 8, okay? This is the p orbital. When you hybridize something, you get something in between. Now this is very directional. This does not cover the entire atom. Again, the green orbitals on here are p orbitals, so you can see that they're very directional. And if we had the third one, it would be just on the px right here. Okay, and that's kind of what would form the sigma bonds here. So they're very directional. So we end up getting a fattened, and we really pretty much ignore that part. This is my hybrid orbital. And it's going to be directional. It's going to be more like a p orbital where it's only going to be kind of going in one way or the other. Okay? So all hybrid orbitals look the same. Only s and p orbitals are involved in hybridization. Okay? So we get these. What we're going to look at today is then how do these hybrid orbitals affect the shapes of the molecules. Okay? Our ultimate goal is trying to figure out what are the properties of covalent substances. Well, we've talked a lot about molecules being polar and being nonpolar. Well, part of that is, do they have polar bonds? Phone call, okay? They have fluorine, oxygen, nitrogen, chlorine. Do we have one of those in it? Okay? But the shape of the molecule also has a big deal on whether or not the molecule is polar or not. And the shape of the molecule is going to be dependent upon these hybrid orbitals. But it's going to follow a general trend. All right, so today we are going to look at the valence shell electron pair repulsion theory. The valence shell electron pair repulsion theory. I touched on it yesterday. We were talking about the shapes and some of the bond angles. Now that's very long and hard to say. So we're going to abbreviate that as Vesper. Even though it doesn't really spell Vesper, the E's in the wrong place, we're still going to call it the Vesper theory. Okay? Valence shell electron pair repulsion theory. The name is self-explanatory. So what do you think the valence shell electron pair repulsion theory says?
Valence shells repel.
What repels?
The electron pairs.
The electron pairs, the bonding pairs. The electrons in their valence shell are going to repel and try and get the maximum distance apart. Okay? So, when we look at, okay, we'll say when atoms bond, the valence Since electrons repel each other, and rearrange to get the maximum distance apart. I dotted my S. Sounds more complicated than it really is. If we have CH4, what would we say our AX formula is on that? AX4, right? And what type of hybridization does that give me?
SP3.
SP3. That means that I have 4 equal hybrid orbitals. Right? 4 equal hybrid orbitals. So how are those 4 things going to repel one another to get the maximum distance apart? Well, they're going to go in all 3 dimensions, and they're going to push, and they're going to form something that looks like this. Okay? Where here's the carbon in the center. These are your 4 equal hybrid orbitals, being very directional in just one given direction, and then your hydrogens coming in forming the sigma bonds. So my venture guess is what we call this shape. Well, I got atom bombs going on here. What's this shape going to be called? A tetrahedron. Okay? I think it's the shape is a tetrahedron, or we say it's tetrahedrally shaped. Okay? I think is the proper grammar on that. I'm not convinced. Okay? So, 4 equal hybrid orbitals, 4 electron pair domains. Okay? 4 places around the nucleus where the electrons are going to be, whether it's a bonding pair or a lone pair. You have 4 pair of electrons around the central atom, the octet. It's going to be in this arrangement. Okay? So, 4 equal hybrid orbitals will arrange in the shape of a tetrahedron. A 4-sided hedron. Now, I kind of showed a little bit of this yesterday. Did he decompose these, I guess? He did. Oh, I love my student teacher. Okay, so if I look at CH4, it looks just like this. This is the shape of a tetrahedron. Okay? It's a 4-sided pyramid. 1, 2, 3, 4 faced. Notice that it's perfectly symmetrical. Doesn't matter which way you turn it, it's always going to be the same. All of the bond angles are identical. The bond angles with bond angles, keep adding to it, of, anybody know in a tetrahedron what that bond angle would be? No, we talked about it. 109.5. Okay? And that's the one you kind of have to know. Now, what if one of them's a lone pair? What do we know about lone pair? It closes the umbrella. That's kind of the way I look at it. Okay? Why? Why does this take up more space? What's there more of? Electron repulsions, okay, because there's no positive up here to kind of balance out some of the negative. So lone pair occupy a little bit greater space. Now, you do not have to know specific angles as far as, you know, what it goes down to, because it's going to depend upon every molecule is going to be different. You just need to know it's 2 to 3 degrees per lone pair. I think you guys wrote that down yesterday. Okay? So it's 2 to 3. So if I look at this one, so this is ammonia, notice I still have 4 pair of electrons around this, 4 electron pair domains. 4 places the electrons are around the carbon. But one of them's a lone pair, but they're negative, they're still up there. But when we say the shape of the molecule, we're going to say the shape is pyramidal. Some say, more official, trigonal pyramidal. So it's a 3-legged triangle versus a 4-legged pyramid. Okay? And so it's trigonal pyramidal. So we don't count the lone pair in the shape, but the lone pair are definitely affecting the shape. If these lone pair weren't here, well then these could come up and be flat and just be at 120-degree bond angles. But the lone pair occupying this space up here still pushes a force down. We just don't call it, use it as shape. Okay? So if I go, and this one is AX4, make sure I'm in the screen please, y'all. If I do AX3E, okay? AX3E, how many pair of electrons are still around the central atom? 4. It's still sp3 hybridization. Right? But one of them's a lone pair, so therefore the shape is equal to trigonal pyramidal with a bond angle approximately 107.5. Give or take. Okay, it could go down to 106.9, could be 107.8. Okay, just slightly less than the 109.5. That's all you need to know, that it's less than 109.5. What if I'm AX2E2? And by the way, an example of this would be ammonia, NH3, and you have that in your notes. And then this one would be water. Again, how many pair of electrons are around the central atom? How many electron pair domains are there? 4 still. So now we have 2 lone pair. 2 lone pair. I know it's right here. I know it's right here. Where'd I put it? Oh, I put it over here. Why did I do that? So now I have 2 lone pair. Now notice the electron pairs are still at the points of a tetrahedron. But we only have these 3 atoms that are still present in the molecule, so we say the shape of the molecule is bent, but the electron pair geometry is still tetrahedron. Y'all seen the difference between electron pair geometry and the shape of the molecule? 4 pair of electrons are always at the points of a tetrahedron, so there's only 1 electron pair geometry for all 3 of these. We say the shape of the molecule now is bent. It's still sp3 hybridization. Okay? But the shape is going to be bent with a bond angle about what? Around 105. Okay? Give or take. Okay? It could be 103.8. It could be 106. Anywhere in the range, depending upon what atoms are bonding. Just 2 to 3 degrees less per lone pair. AP on the test, they give you a wide range of possibilities on what these bond angles are going to be. Okay? So, that's the most common shapes, because that's your filled octet. Okay? But what if we have 3 areas, AX3? like sulfur trioxide, the very first one on your sheet. Now how many areas of electron domains do we have? How many different places are the electron densities going to be? 3, not 4. The reality is it's sigma, 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 pi. The sigma bonds are what's going to determine the shape. The pi bond's just going to be that perpendicular one that's going to overlap side to side. It doesn't really affect the shape. The sigma bonds affect the shape. Okay? So sigma bonds affect the shape. I'll say determine. Sigma bonds determine the shape. Okay, and then just for terminology, we say there's 3 electron pair domains. And a domain is where the electrons are hanging out. There's 3 places where the electrons are hanging out. In these other ones, there are 4. Okay? So what's the type of hybridization? sp2 hybridization. And what shape do you think that 3 things that hate each other are going to try and get to? A triangle. Okay, and by definition, triangles are flat, so we're going to say the shape is trigonal planar. Okay? What am I doing? SO3. Okay, so here's an SO3 molecule. Okay? Notice it's a totally flat molecule. 3 points define a line, but there are actually 4 points here, which is why we can say trigonal planar. You have the sp2 hybridized orbital here, here. The first bond of this is that hybrid orbital. Then you have a p orbital perpendicular and a p orbital perpendicular overlapping side to side to form the second bond. Okay? So it's the sigma bonds that determine the shape. We say that there's a 3 electron pair domains. Now what's the bond angle? This interior bond angle of a triangle. 120. So it has to add up to 360, right? 120, 120, 120. You guys remember that from geometry? Okay? So the bond angle is going to be 120 degrees. Okay? More spread apart. Atoms kind of like this because there's a little more space, there's a little bit less electron-electron repulsions. But now, what if one of these is a lone pair? So we go to AX2E. Still, how many electron pair domains do I have? 3, right? Okay, so I can say SO2 in this case. But one of the electron pair domains is the lone pair. But they're still occupying the points of the triangle. Okay? Still occupying those points. But when we say the shape of the molecule, we only play dot to dot with atoms that are actually present. So what's the shape going to be? Okay? So it's still sp2 hybridization. Okay? So the shape is going to be bent. And what's the bond angle going to be? 117 to 118. And it's actually going to probably be closer to 118 because there's more space already. So the electron-electron repulsions aren't going to have as much of an effect. Okay, and so it's gonna be the bond angle, and again, you don't have to know exact, you just need to know it's gonna be approximately, 118 degrees. Approximately. Okay? What if we have AX2? There's only two possible shapes there. And by the way, whenever we get to just the AX, what's the only shape 2 points can make? A line. So anything that's diatomic, just two things, H2, F2, Cl2, Br2, even HCl, anything that just has two atoms, it's going to be linear. 2 points can only make a line. So we don't ever have to go down to AX. Okay? So now what about AX2? Something like carbon dioxide. Okay? Or HCN. Anytime you have a triple bond, it's always this. It's always what type of hybridization? SP hybridization. Okay? You only have two sigma bonds. Sigma, sigma, pi, pi. Two things that hate each other, what's the only shape they're going to get to? 180 degrees, right? Okay, so these are always linear. And then the bond angle, 180 degrees. And there's no way, we don't even go down, there aren't any more options than this, it's just one option. So two double bonds or a triple bond is always going to cause it to be linear. Okay? Now, if water was linear, I talked about this, water was linear, it wouldn't be polar, it wouldn't be a liquid at room temperature, and life as we know it would not exist. The only difference between water being a liquid and carbon dioxide being a gas is the fact that carbon dioxide is linear and water is bent. Non-polar versus polar. Weak London forces versus much stronger hydrogen bonds. Okay? Little difference in the shape cause a big difference in the properties. All right, real quickly. What if we have an expanded octet? Okay? What if we do AX5? Okay? AX5. Something like BRF5, I think was a 5. Bromine, that's going to be 30, what is that going to be? 7 times 6 is 42 electrons. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, miscount, 38, 40, miscount, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, shoot, this isn't one. Sorry. That's going to be an AX5E. PCl5, that'll work. PCl5. Sorry. Okay? AX5, an expanded octet. 5 things that hate each other. What shape could they possibly form? It's going to be called, let me see if I can find the right one. Might be easier to find than this one. Yeah, here we go. Just so you know, you guys are about to play with these. Okay? 5 things that hate each other. This is called trigonal bipyramidal. It's a 2 pyramids with a triangular base on top and a pyramid forming on the bottom. Trigonal bipyramidal shape. Okay? Trigonal bipyramidal. Now, we got 2 different bond angles. What's the bond angle going to be in the triangle? 120. What's the bond angle going to be here? 90. So we have bond angles equal to 120 and 90. All right. But what if we have a lone pair? Okay? Anyone want to venture a guess where the lone pair would most likely be?
On one of the poles.
On one of these, here or here? Because you would think it's farther apart, right? But what's the bond angle here? 90. So it's a little bit more crowded. What's the bond angle here? 120. So we have a little bit more space. This is called the axial position. This is called the equatorial position. I think that makes just sense on that. So the equatorial position is where the lone pair is going to come from. Because the lone pair has more space, it's less crowded at the 120 degrees than it is at the 90 degrees. So now if we are if we go to AX4E, the good news is with expanded octets we don't have to worry about hybridization. AX4E, the shape's going to be it doesn't make a shape, okay? It doesn't make a shape. It's called a distorted tetrahedron. Okay? A distorted tetrahedron. But someone said that's too complicated. It really just looks like a seesaw. Okay? Looks like on the playground, the seesaw, I see you, I saw you, I see you, I saw you. Okay, so an official scientific name for this shape is seesaw.
What? That's pretty amazing, not gonna lie.
Why can't they just name it?
Okay? Now, what if there are 2 lone pair? What if it's AX3E2? Well, again, the lone pair is going to come out of the center. Okay? What would be a good name for a shape, this shape? A T. It's a T shape. Okay? Like Mr. T, I pity the fool. Okay?
Mr. T.
AX3E2 is going to be T-shaped. Now what are the bond angles now all? 90 degrees. We still have 90 and 120 on this one. And then where obviously will the last one come out of? The third. I have it right here. Okay, so it looked like this, so what shape is this going to be? Linear. So AX2E3 is equal to linear with a 180 degree bond angle. So the key on this is that they all come out of the equatorial position. But it's all based upon the hybrid orbitals, the electrons trying to get the maximum distance apart, they're repelling, they're maximizing orbital overlap, and minimizing electron-electron repulsions. That's the whole goal. okay? Because you get more stable with the bonds and the electron-electron repulsion is minimized, makes everything more stable. All right, one more round. AX6. 6 things around it, okay? This would be like sulfur hexafluoride. Have any of y'all seen late night TV, 1, 2, 3, 4, 5, where they bring the science guy on and he does demonstrations on like the Tonight Show or late night, you know? One of the things that they do is, you know, if you breathe in helium, you talk super high. Sulfur hexafluoride is very, very dense gas. If you breathe it in, you talk super, super low. Okay? They can also, they fill up an aquarium. This gas is colorless, but they fill up an aquarium with this, but because it's so much heavier than air, it just sits at the bottom of the aquarium, and then you can kind of float things that wouldn't normally float, just in the very dense air. So it's kind of a fun one to play with. I looked up the cost, and it's very expensive, so I can't buy any for demonstrations. So, okay? But 6 things. 6 things that hate each other. Where's my 6 things? Right here.
I want some so that I could just take some every morning. Yeah. Still on the moon? The moon. Yeah, I already sold it, right? The last time you saw the moon sky. It's not huge.
Okay. 6 things that hate each other. Now, they call this one trigonal bipyramidal. I would have called this one square bipyramidal just to have some consistency. But it's an 8-phased hedron, so it's going to be called octahedron. What's the bond angle going to be? 90 degrees everywhere. 100% symmetrical. Okay, and the symmetry is real important. 100% symmetrical. Now, therefore, when I go to make a lone pair, pick one, any one. Doesn't matter. Okay? So now I have the lone pair. Now, what's the shape going to be, you think? What type, what's the base? Square pyramidal. So AX5E, still 6 pair of electron pair domains, it's going to be square pyramidal. But the bond angle is still just 90 degrees. It's never going to change. Now, based upon what we've talked about before, where do you think the second lone pair is going to be? What'd you say? Yeah.
The other pole.
The other, the one opposite of this, I think that's what you were implying. Okay? Because again, the electron pairs are going to want to get maximum distance apart, because there's the greatest electron-electron repulsions there. So what's this shape going to be? Square, planar. So, when we talk about electron pair geometries, we only have, what, 5 of them? If it's SP, it's going to be linear. If it's SP2, it's going to be trigonal planar. If it's SP3, it's going to be tetrahedron. If it's AX5, it's going to be trigonal bipyramidal. And if it's AX6, it's going to be octahedron. If you have those many electrons hanging around, the valence shell electron pair repulsion theory says those electrons are going to shift and move to be the maximum distance apart. And those are the shapes that will be the maximum distance apart. If there are 2 pair of electrons, 2 bonding sites, 2 sigma bonds, it's going to be 180. 3 sigma bonds, 120 a triangle, trigonal planar. 4 sigma bonds or lone pair, it's going to end up being tetrahedral. Now, the shapes of the molecules vary. Now, you guys wrote all that down.
They're fun. That's nice. I guess that I did this. Huh? I guess that I did this one plus. I think I'm just worthless. I think we're getting not yet ready.
So everything that we just talked about is on this sheet. Okay? Notice that they're broken up into the different sections. So in terms of electron pair geometry, all three of these at the top are octahedron. Electron pair geometry, the electron pairs on this one, no matter whether the bonding pairs or lone pairs, they're going to be arranged trigonal bipyramidal. The electrons on this one are all going to be in tetrahedron. The electrons here, trigonal planar, and here linear. Okay, so we need to always differentiate between electron pair geometry, and a lot of times the AP uses the word electron pair domains. And a domain is just a place where the electron is going to be. And it's the sigma bonds that determine that. All right, now, using this, I want you now on that same Lewis dot structure worksheet, I want you to go through and tell me the shape around for each molecule. Now, let me just give you this. When you have a molecule, this is your HNO2, and that by the on the screen. HNO2. There are two central atoms here, so you give the shape around the nitrogen and you give the shape around the oxygen. There's not just an over-molecular shape. So you give the shape around each central atom. Okay? So you don't just try and say the shape of the whole molecule, you have to look at each central atom. Most of them only have one central atom, but if it has two or three, you have to give the shape around each one.
Okay, so what would it be for that one?
This one right here?
Yeah, for like O.
What would be my AX formula in this? AX2 E2.
Uh-huh.
So you go to your sheet. Now again, remember the AX is never an answer, it's just a code to get to the answer. So what's the shape going to be?
And
Bent. Bond angle is going to be somewhere in the 105 range. Those of you watching at home, please take the time, do the assignment on the worksheet right now, okay? And then I'm going to come by and check it, and you guys need to submit it by the end of the day, those of you at home.